Okay, so the first seminar in the seminar series for this academic year. I'm very glad to welcome Amir from Columbia University and Google, who will tell us about causally driven ML for text data.
Hi everyone, happy to be here. So today I'm going to talk a bit about my research on causally-driven ML. There's an asterisk for text data. We're going to see the details for why text makes it a bit easier and sometimes a bit harder. And
במיקרופון? לא, לפי הסאונד. תקים ממנו.
All right, okay, so let's go ahead and start this. All right, so causal inference, or the need or the desire to understand how variables affect one another in a causal way, is a pillar of scientific thought, including social sciences and life sciences. And it has been a part of the way we think philosophically about the world since antiquity and through the Enlightenment. And in the late 20th century, it was formalized into two distinct but connected schools of thought that try to provide a mathematical formalism and a bunch of methods that rely on it to kind of try and build a scientific way, a concrete way that allows us to understand how variables interact. And all of this is centered around our need to, or desire to infer causal effects of treatments. Something that, let's imagine a pill that we're giving a patient, we want to understand the outcome of giving the patient that pill. At the same time, machine learning, and specifically I'm going to talk mostly, when I say machine learning in this talk, I'm going to mean mostly deep learning, is doing perfectly fine with it, without it. Right? There's no explicit thought being put behind large language models and other models to kind of think about causal relationships. And still we're seeing like very, very strong results through ChatGPT and large language models very broadly. And also when we think about other modalities like images, diffusion models are always also doing a very good job at understanding the world and making predictions without any explicit causal understanding. And this especially works well when we have massive unstructured data set. I'm going to mean that when I say unstructured, I'm going to mean that we need to learn the features before we make predictions. So it's not that we're getting very easily identifiable concepts like we're getting in causal inference. And yet, I'm going to argue throughout the talk that machine learning models are untrustworthy. I'm sure you've heard this mentioned in the past. I'm just going to talk about two specific aspects where I'm finding this untrustworthiness of machine learning models. There are obviously more. So the first is interpretability. For example, in an early research of ours, we have successfully shown that you can predict the actions of NBA players in-game from their pre-game interviews. And this could be this is above and beyond what experts in the field could predict. And you might think, all right, this is a good finding for social science, right? We can understand something about mapping from language to subsequent strategic behavior. But in fact, you just take the models that you're going to use to predict those actions, you'll be hard pressed to find anything that tells you something about what it means to map behavior to language. And just looking at the weights of a prediction model that takes text and outputs some outcome in the game, we can't really understand what's going on. So just to summarize, it will perform very well in distribution. So if I want to predict other games from LeBron James, I will do a very good job, but it's unclear what the model is learned about, fundamentally about the world. Another issue, and this will be the main thing I'm going to talk about in today's talk, is robustness. We see here a tumor classification problem. We have data sets from multiple hospitals. And if we try to classify whether there's a tumor or not in those images, and we do it across these training hospitals, there's B1, 2, and 3, we could have a very successful model in the sense that it will have very high accuracy on a held out set from these hospitals. But in fact, if we take this trained model and deploy it on an unseen hospital, it could fail miserably. And this is what they found back in 2018, and this has been a data set that's kind of the pillar of this field since. So this kind of failure mode that we're seeing, where models perform incredibly well in distribution and fail completely out of distribution, has been linked to the ability of these models to rely on shortcuts that they find in the data. a simple example you can think about is just maybe the specific details of the signal that was captured, maybe the hue of the camera, and the technical details of the hospital, but also the specific distribution of patients that we're seeing in the hospital. Yeah.
I have a question about the left-hand side.
Yeah.
How strong and robust are these observations? I mean, I guess the interviews are very limited in their vocabulary anyway.
Yeah.
So, what's the connection between this and?
Exactly right. So you can make.
prediction?
That's a great point. So obviously you could you could
So I
design.
didn't mean to be racist. It's like models and footballers. I mean, they.
There's like there's like a famous statement of Yao Ming, and Burnett sitting in the All-Star game, and somebody asked, and somebody said like the person doing the TV show that says like, here's three people who don't understand English. So yeah, they have a very limited vocabulary, but it is still very predictive. So you can look at it at face value. We have a model, we have an accuracy result, we can do a lot of robustness tests to it, and you can see that still the model is pretty robust in making better predictions than alternative baselines. You can leave it with that. Now, if you care about the actual task and you say, what did I understand? There's something this model has captured about the world. I don't know what. Now you'll be hard pressed to take that extra step and then say, what do I understand fundamentally about human beings and how they interact in the world? All right, so this failure mode of models being on shortcuts is something that we're going to try and solve. This is kind of a preview for the future. All of these problems, other problems are problems of privacy, problems of fairness. All of them lead to kind of the inability to trust them in isolate scenarios, and the data sets and the models that I'm going to show you that are deployed are in healthcare, but I work a lot on social science as well. And specifically, the lack of interpretability and kind of uncertainty estimates for the model hinder our ability to do science. So especially in the social sciences, if we want to have, if we have a causal question about text, it's going to be very hard for us to use these types of models. All right. So the main question that my research tried to answer, you can think about this in that direction. It's about using ideas from causality to help these types of problems in machine learning. So if we go back into those two examples that I gave, in the case of trying to predict actions from language, we can think about this problem as a problem estimating causal effects, but on models, not on the world. We have kind of a smaller request here from the world. We just want to understand what the model is doing causally and not what the actual mapping between actions and language. And if we define it as a causal problem, there's a lot of methods that we can build to estimate the causal model effects. And this is a previous research that we have done. And in the case of removing these non-causal features, those shortcuts that models tend to rely on, and because of that fade-out distribution, there's been a lot of literature on kind of trying to think causally about this problem, a lot of distribution, and a lot of methods that were proposed, and I'm going to focus on two of them that we used. I'm also interested in the converse relationship, and this is how machine learning can help causality. I'm going to touch on that very briefly at the end, just to give you a taste of what we can expect to do in the future using machine learning to help people that care about causal effect estimation, and that's going to be specifically tuned to problems like with text, where the world is not very easily represented with our raw features. So the roadmap for today's talk, I'm going to spend most of the time focusing on the single problem of improving robustness through removing these shortcuts in models. I'm going to give you the causal story for why I think causality has something to do with this problem. And I'm going to briefly mention one method that we have introduced during my PhD, and spend most of the time showing you a new method that we've developed in my postdoc to solve it. I'm then going to give you a taste of the conversation. So let's start. So let's start with considering an actual problem. We have data. We have data from a single hospital. It's called NIM3 for anyone that's worked on a medical data set. It's an electronic health record or an EHR. Unfortunately, due to privacy constraints, we can only train our classifier on this single hospital. And what we're going to need to do in the deployment is we're going to take this trained classifier and use it on whatever hospital we get. We don't have, we don't know which one, and we don't know what's going to be the next. But within that hospital, we have a lot of information. We know the entire journey that patients go through the hospital. We know that they're doctors, we know their prescriptions, their medications, their lab results, all of that. And we're going to leverage all of this information to build a solution. And the solution that I'm going to propose later in this talk is the one that's actually being deployed for this problem. All right, so let's imagine two of the doctors within this hospital. We have Dr. Alice and we have Dr. Bob, defined as I and J. They are different in two aspects that are interesting for us. First, they receive a different distribution of patients, and we can discuss later on why this is happening. And another thing which is important is that they write notes in a different way. It could be because Dr. Alice has a template that she uses in her computer. It could be because Dr. Bob has a specific dialect, and because of that writes English in a certain way. But what we're left with is some connection between the content of this note, of the text in that note, and the label to be what we call spuriously correlated. So there's going to be a shortcut in the data that the models could use. For example, the type of dialect, like an Australian dialect here, could be associated with arrhythmia by the model, and the template for Dr. Alice could be associated with ear infection. And if this happens enough times, if the distribution for patients for Alice is different enough from the others, models will pick it up, and especially large models are very good at picking up these nuances that even we, by looking at it, by observing it, would never find. And this exact failure is what will cause the failure, the failure model distribution. So if you can imagine, we have a new hospital, we now have an Australian doctor that gets a patient with an ear infection, models. Right? This is obviously kind of a very simplified example, but this in fact does happen. So we have what's very common in the US is that you have different dialects across regions within the US. The language is very different, and also different distribution of patients. For instance, in a Texan hospital, we have a much bigger, much larger distribution of patients with diabetes compared to Beth Israel Hospital in Massachusetts, which is the hospital we're training on. All right, so I gave you kind of foreshadowing that I think causality provides a formalism and some methods we might want to rely on. So pointing to these two schools of thought, from Yuda Perro's causal graph, we're going to use the graph structure. We're going to use a probabilistic graphical model to kind of encode our assumptions and show us what we can and cannot do, and also what we need to do. And I'm going to use the potential outcomes framework by Don Rubin to kind of think about the problem here is a problem of missing data, right? The problem that we have here that causes our issues is that we never observe the same note written by different doctors, right? We only have what's actually observed and not what could have been had the note been written by another person. All right, so if we take the causal graph and think about the problem that happens here, the problem is that condition Y causes caregiver assignment, right? If I enter a hospital and I say to the person in the reception that I have something in my ear, I have some pain there, I'm more likely to be assigned to Dr. Alice than to Dr. Bob, and this might cause this for this solution. Right, and you can think about this model, and we were going to continue on with this graph. We have the doctor ID is E, the outcome Y, and the note. We're going to talk about what does it mean to have this X represented from text as SX. All right. So thinking about potential outcomes, about this missing data problem, we could also imagine the ideal training distribution, right? If we could have had an imaginary hospital where I enter the hospital and I'm either randomly assigned caregiver, completely random, or conversely, I'm just seeing all of the doctors, right? I'm just going through and passing through all of the doors in the hospital, and I get the same, for the same condition, I get a note being written by all of the doctors. If I had this training distribution, surely the model would have no reason to rely on these shortcuts, and it will also generalize better when the world changes, right? So this is what this will be the ideal training distribution. We obviously don't have, right? We just get to see the observational data that we have from this single. That's interesting. But so their final goal would now be, yeah, this is an interesting. The refined goal will be to approximate this world, right? We never get to see it, but we want to get as close as possible. All right, so in identifying kind of this problem, not in the context of this specific hospital issue, there have been a lot of methods that try to leverage the fact that we get to see multiple environments. Ideally, there will be multiple hospitals, but because of privacy constraints, what we do have is we have multiple doctors, right? And what we will try to do is to leverage the fact that we see different people writing the same content to weed out what's causal, what's always there, and what's spurious, what's changes across different characters. So the kind of the seminal work that opened up this research on causality and machine learning even more broadly, it's a paper by Peters et al. And the crux of it is showing that prediction on multiple environments can remove non-causal variable and even allow us to do causal, like exact causal inference if we get to see multiple environments. So this works in a very simplified case. Imagine that we have kind of this well-interpretable X variables, and they have some known interaction with an outcome Y. And let's say we can even say exactly what they are. Imagine where we're trying to predict whether a person will be late to school, and we have all of these variables. What they're doing there is if we can imagine getting to observe maybe two different cities, two different locations, where there is either a traffic accident or there isn't one. And you can also imagine a world where when the person gets up late or doesn't get up late usually. If we get to see all of that, then we can design algorithms that will end up only using X2 and X4 for prediction, and that model will be stable. We might lose something in predictive power within distribution, but this model will generalize very well as the world changes because it only uses the direct causal ancestors of the thing we want to predict, which is 1. All right, so this is very fine, but this works in a very low dimensional, kind of nice causal inference way. When we do machine learning, it gets very dirty. For the first thing, we can't really say what's in X, right? X is a bunch of words, it's a bunch of pixels, it's not easily interpretable. And can this be just decomposed, right? We can't X ante say to the model, these are the parts of the text that matter, these are the parts that doesn't. So kind of moving that into kind of the last couple of years, people have tried to alternatively think about how can we use this graph to enforce independence from the environment. So how can we learn a representation of the text denoted as phi of X that is conditionally independent from the environment? You could do this through regularization. You could do this through reweighing, such that examples could come from doctors that are very correlated with some outcome get way less. But all of these problems are kind of so this is the reweighing that we can do. But all of these problems are kind of very hard to optimize. What we're trying to do here is we're trying to learn a representation such that that representation is independent of this E variable. We don't get to know the decomposition of X, and we're left with kind of a mesh of a task that's incredibly hard to solve and also has very high sample complexity because of this reweighing. We're essentially decreasing the effective sample size. And this is quite inefficient and leads to the problem, which we fear the most, which in theory, we can have a lot of very nice promising results about kind of testing this link between causality and machine learning. But when we take this to real world problems, and that doesn't even have to be like a tumor detection or a condition classification task from nodes, it would be a very simple task. We end up not really improving much. So we had a good theory, it's all nice on paper, but it doesn't actually solve what happens. All right, so kind of the first my first dip in these waters, trying to overcome these challenges in enforcing independence, came through my PhD in New York's 2021. What we have kind of discovered and tried to think alternatively is that instead of thinking about enforcing this conditional dependence, let's think about other machine learning tools that we can employ that will get us to this independence if we get to satisfy them. And one thing that we have identified is multi-environment calibration. So if you think about data is coming, this could be from different hospitals or from different doctors. If we can get a model to be well calibrated, meaning that true probabilities match the predicted probabilities across all of them, then we can prove that this will get you conditional dependence. And we got also a good criterion for you to decide whether the model is going to generalize well. I'm not gonna I'm not gonna put too much emphasis on theory here, but what we try to do is prove in rather simplified setting, and it's been expanded since, but in our paper that was quite simplified, that if you have a multi-environment calibrated model, meaning that you're equally you are calibrated at the same time on all of these doctors, then you would get to be conditionally independent from the doctor. And as the number of environments increase, so as we get to see more hospitals and more doctors, we will remove more shortcuts from the model, and the model will generalize better. And we propose some methods to do this proactively, so achieving calibration with some regularization that pushes us through calibration, but we don't have to do that even. We can just look at a couple of models and select the one that has the best, on average, calibration score across the different environments, whatever your environments are.
Question.
Yeah.
Seems like it's related to like notions of fairness when you try to calibrate on the same. And so,
Yeah.
do you need to identify the environments by yourself before something?
Perfect. So that's a great point. So there is I talked about robustness, but we can think about this mathematical formalism as almost directly being able to push over to fairness. There's a lot of comparisons there. The literature is quite connected. In fact, counterfactual fairness, the causal version of this literature is very similar. One thing that is kind of transferable here is, yeah, we are imagining that we observe the doctor ID. It's not like we're imagining that the difference that we care about is the ID. We're imagining a more latent variable, or we're imagining the style of the doctor, something like that, or the style of the camera. But yeah, we're assuming that we have some observed variable that is connected to what's defining our groups. So in fairness connection, there will be we observe the ethnicities or the races of the people that are in our data. Anyway. All right, so this is useful, I think so. First of all, because it's easier to learn, right? We don't have to get into the pretty details of doing conditional dependence testing, which is very hard and very demanding. And we can plug it into any OOD method. I will show you in a second. And it's very useful for model selection. Basically, we have a measurable measure of expected model performance on our distribution. We just need to see whether the model is equally calibrated across environments, and that will give us kind of a criteria to say something about how that transport to a new hospital. And if we recall that Bandy example from the tumor detection, what you see here in the right-hand side is if you see like in the triangles here, there is a mapping there that as you get more calibrated across environments, so this in the average in-domain calibration or the ECD, as that improves, the accuracy of the model on the held out OOD hospital also improves, right? So regardless of what underlying machine learning method you want to employ to imagine that you're going to get better performance on the that you haven't seen, if the model is more calibrated in the sense that across environments, on average, it is calibrated, you're more likely to perform well on auto distribution. That's why I mean that you can improve it using our method, but you can also just select the model that has better calibration properties, and the same result was then transferred to fairness. So you can say the same thing about having a fair model across protected attributes. So there's still problems with it. Specifically when we have a low number of samples per environments. For example, we have a doctor with only rows of pen notes. This is going to be very hard for us to learn, and it's going to struggle. And maybe the main thing that kind of caused me to push this further is it doesn't solve the clinical note classification. So the problem that I started with, where we have a single hospital, and we just hope to do as well as possible on the unseen hospitals, it doesn't solve. This could be connected to the low amount of samples, but you can take it just as face value, it doesn't work. Another point, and this is kind of connecting us with the times, generative models that I've tried to talk, I've made some good arguments for them, like large language models, are improving in a very rapid pace. We're not doing anything, right? We're solving a task with text. We're not doing so far anything with them. And the question is, can we utilize them as part of the process? Can we think about kind of a concrete, causally driven way to harness them as part of the algorithm, such that we'll be left with a better solution at the end. And this is what I want to focus on mostly. You can think about the ideal training data that I've mentioned in the past, and then a few slides ago, right? We have so far observational data. We have just what we have from the hospital, and we wanted to enforce independence either directly or through calibration. So the goal was to have a representation of text that's independent of the doctor. But an alternative that kind of connects us to this potential outcomes definition is that we can just approximate the same ideal training data, right? We don't get to see the same doctor visiting multiple doctors, but we can definitely track the results. This will surely introduce some bias, some problem in the algorithm, but we can also think about this in a concrete way. So you could also say that this is just augmentation, right? For those of us who have worked with deep learning models in the last couple of years, augmentation has been proposed as a one fits all solution to everything that we can imagine. Just generate more data from a large language model, generate more data from a diffusion model. I'm going to say that it's more nuanced than that, but at least it gives us a reason to try it. All right, so augmentation in the context of images, that'll be the simplest case. Let's just rotate the image. We know that this should keep the label, and the model should be able to predict equally as well on all of those images of objects. So this will be quite general in the sense that you can think about a lot of different causal structures, a lot of causal models, where in principle, if we could have generated these counterfactuals, it will solve our problem. And it will have a low sample complexity, meaning that for the same amount of data, it should perform well. I'm going to show this in a couple of slides. As I said, it's hyped up, but when we go about it in practice, we try to solve important problems with augmentation. It's going to be very hard, especially with text. It's going to be very hard for us to just take a note from a specific doctor and imagine that we just flip it to another one without changing anything of importance. But again, this is a unique opportunity, and I want to at least explore the problems that it's there. And so the solution that I'm going to propose based on that is two causal estimation techniques. So to try to generate a counterfactual quantity that no hadn't been written by another doctor, but we're going to use representation from a strong generative model to make sure that this happens in a correct way. And again, this is all boils down to imagining this ideal distribution where doctors are assigned randomly. All right, so let's formally define the setting. We still have this three observed quantities. We have the outcome, we have the caregiver ID, and we have the clinical note. They are somehow correlated. There could be a lot of mechanisms to describe why they're spuriously correlated. One of them is the assignment mechanism that I've described. But we also imagine this unobserved variable, I'm going to call it X star. It's going to be the effect of the outcome. So you can think about this as the portion within the text that is causally relevant to the outcome. So it should not contain style, but it should contain any clinically relevant information within the note. And we're gonna try and get the model to only learn X star without the other portions of X that might be coming from this unwanted relationship. And if we think about all of the causal interventions that we can do on this thing, we're left with this factorization where one thing is unstable, right? The probability of E given Y might change across hospitals, but all of the other things are stable. All right, so a learner is given these three things, at least in training time. We get these X's, Y's, and E's, and their IID drawn from some p-train within the APP. All right, and we define formally the ideal distribution or the independent P as being given from a world where caregivers are drawn random. So it's you get to a hospital and just randomly gets a caregiver regardless of his specialty. And we can prove through the desperation causal tricks that the Bayes, this is quite straightforward, that the Bayes optimal classifier under this ideal world would get the same accuracy across all of these. So because it's not using any of the information about P of a given Y, this model will have the same accuracy and it will be max optimal with respect to this distribution that I've defined. And the goal is to learn some H star that's given at sample n, so there's some amount of notes from a hospital that's drawn from feature. That's going to be our goal. All right, so just one kind of important sidetrack. We get X is a bunch of words. It's kind of unclear how we get that into a vector representation that allows us to work with. So anybody that has worked on NLP might know this, but for any of us who don't, we start off with just a representation that is literally just the place in the vocabulary for each of the word. We train this next word prediction model and we try to predict this missing word on basically the entire internet, and then some, and we're left with a representation, what's inside there, that we're going to try and use when we get to see the hospital data. So let's say we have some note, we then push it through this model, and what we care about is this intermediate representation. So we're going to be left with a vector representation of the note, and we're going to play some games with this representation. So let's call this one Excel, right? And this is applied to different goals. All right, so we're given Excel, we're given some note from some doctor, and we're going to try to think about what's this tau E function is going to do, which is going to take us from this note and get us to the counterfactual or the approximation of the counterfactual quantity, the note that iterative right above. So then what we're going to do is we're going to minimize loss with respect to this augmented data set. It's going to contain all of our original examples and the examples that we've generated using tau. And ideally, if we have an perfect approximation, meaning that we can actually generate this counterfactual quantity, this will be exactly equivalent to minimizing risk on this ideal independent field. So there's going to be a lot of challenges there. First of all, and this touches on any problem in causal inference, it doesn't exist, right? There's no such thing as a counterfactual note added and written by adopted doctors. We can only approximate it, but we need to evaluate it somehow. And we're going to make some assumptions to allow us to do that. There's thousands of caregivers, some of them with very few notes. I said this might be a reason for why previous methods have struggled with it. But it's surely going to be difficult to imagine notes for these doctors. And learning this estimator tau is also anybody's guess. All right, so we are in 2023. We were told that LLMs can solve everything. Let's just try it. Let's just say to the model, you are a vertical clinician. Here are a bunch of notes you've written before. Here's a note written by another clinician. Insert note. Let's hope for the best. Right? We can do that. You just literally insert all of Alice's notes or select some of them by some mechanism, put a note by Dr. Bob, and hope for the best. But what's going to happen here? Dr. Alice's distribution of patients is different, right? So the blood pressure that she sees is usually higher because she sees older patients. And let's say that Dr. Bob now sees a young kid, which is less likely to have a high blood pressure. The model doesn't know that, but he knows that there is common ground here where blood pressure is quite high. What we're going to get, and you can actually do this exercise if you want with ChatGPT, is we're going to get a model, an outcome that includes a very unrealistic blood pressure. This we don't want. This will surely introduce a lot of bias. If we insert that as an example for our training data, this will surely won't help us to make correct predictions, especially out of the solution. We can think about the causal graph connecting this problem. We have so far an unobserved n variable or metadata, auxiliary data, whichever you want to call it, that we're not using to model our problem, even though it is part of the causal graph, and it does definitely affect what gets written in the text. All right, I said before that we have all of this structure in the EHR, right? We have a journey of patients within hospitals. They get to see multiple caregivers. They get multiple notes written about them. And throughout their journey, they get a lot of information noted about them. And I want to use all of this information to improve the approximation that I'm doing. So the key step is going to be to match using this M information and this E information to improve the causal. So I'm gonna propose two versions. There are gonna be more, but at least here it's gonna be two versions where I'm gonna use the information from the node for its representation. I'm gonna use the metadata that I have about patients and the doctors that they got. And all of this will be pushed inside this tau function to get me the counterfactual of the doctor. And this matching phase is kind of a key aspect of the way we do causal inference, right? It's all about imagining this intervention, imagining a world where we assign this treatment. Let's say this treatment is which doctor you get to see. And to approximate this process, because this is not what we're seeing in reality, what we're gonna do is we're gonna look for patients that are very similar in terms of their observed variables, meaning they have similar conditions, they have similar lab results, maybe their doctors are similar, and best case scenario, we'll get to see two patients with the same doctor that switch, and I'm going to use that structure next. All right, so as I said, this is the spam work. We can imagine two ways of doing it just for the sake of this presentation. In fact, we can take any version of any causal method that gets us to a counterfactual estimator and use it. I'm going to give you the easiest two, but I think they're very interesting. First of all, if we look back in our prompting examples, if we get to match patients that are very similar in terms of their blood pressure, for instance, then we're at least ensuring that the model does not get to change that aspect for the new patient. And this will work maybe in simpler problems. We show in the paper a lot of versions when it does, but this sounds probably too simplistic for many eyes and for me as well. So let's think about this different approach. So imagine we have two similar patients. That they're not only similar in the sense that they have similar conditions coming into that spot in their hospital journey. They also have the same doctor. Both of them start with Dr. Bob. And and when they get moved from this T-1 stage to T, something happens. Patient I switches to Dr. Alice, while patient J stays with Dr. Bob. If we get to see the structure, and we get to see it quite often in a hospital because of that journey that they get, we can leverage this structure, making some additional assumptions, and imagine more clearly how this counterfactual quantity. So if we can imagine this kind of constant effect of what happened to patient J, which stayed with the same doctor, we can imagine this counterfactual quantity for patient I, if he would have stayed with the orange doctor, with Dr. Bob, to be this kind of algebraic manipulation of taking the representation of the node before, plus the difference between post-treatment and after and pre-treatment for the patient J. Right? We call this diff and diff, or differences and differences estimation in causal inference. But in fact, you can imagine, for those of you who care about causal inference, synthetic controls, instrumental variables. There's a lot of approaches we can take here, but this is still kind of simplified and also works. Right, so we can do this manipulation game for both of these counterfactual quantity, patient I under Alice, patient J under Bob, and get two new examples for our training set that hopefully kind of disconnect the connection between doctor style and the outcomes that we're observing. All right, so we need to make some assumptions to allow us to estimate or say something concretely or theoretically about this. I'm gonna make two assumptions here that are quite common for causal inference. One is no given confounding, meaning that once we have all of this metadata about the patient, there is nothing else that we don't get to observe that also affects treatment assignments of the doctor that we're seeing. Obviously, this is false. There could be many reasons for why in a hospital patients switch doctors. We don't get to observe it. We don't get to see all this information, and this might worsen our results. We also assume positivity, that the probability of getting some metadata is always positive. But given those two assumptions, what we get to do is we get to express this counterfactual unobserved quantity of X hadn't been by Dr. E. We can now say it in terms of quantities that we get to see, right? We get to see M, we get to see E. This is just a conditional probability that we can think about. And the consequence of this is that any distance measure between this ideal counterfactual probability distribution that we don't get to see and what we are approximating is going to be estimable from data. You can think about this as we're going to be able to say, given a new node that we have generated, how similar it is to the distribution of that doctor we try to generate. Right, then we can design two sample tests that will give us some difference quantity, and this is important because this distance is going to be in the sample complexity argument that I'm going to show next. All right, so in simulations we can see that obviously this distance is never going to be zero. We're always going to make a lot of errors because the assumptions, also because this is a hard thing to do, but. And as a matter of fact, if you compare to actual working solutions from that literature and slowly introduce more noise, meaning that we have here that we know the perfect way of generating this counterfactual, this simulation, we introduce more noise, we increase the distance between what we're generating and what would have been the optimal one. And even with a substantial amount of corruption, we still get a better solution than alternative approaches. And I'm going to show you why this happens in terms of why we think it happens, and this will connect to the sample complexity argument. So what we show, and again, I'm going to spare you the theoretical details, is that the distance from this ideal distribution in terms of risk has to do with this, again, this distance, which we can think about and estimate from data to some extent. And if we kind of take a further step and take previous approaches and try to also produce for them a similar sample complexity argument, we see that this is the best alternative solution. This is reweighting that I showed you in the beginning. We get arguments here that are dependent on the underlying correlation between Y and B. As this gets larger, this will irreducibly increase your sample complexity. And what we're doing when we're reweighting is just essentially decreasing the sample set. Right, so this is just a ring divergence. You can see it like comes up in two terms here. But what this comparison allows us to do is to think about what's the gain here. So as the approximation improves, as the distance between counterfactuals and our approximation improves, the generalization gap will scale with n over minus half, and we can get a factor of this divergence in sample complexity. And as we will get data sets where this is more profound, you have more correlation to begin with, this will get us a much better performance, and you'll see it on the actual data in the next thing. However, unlike kind of the main arguments that are given in the augmentation literature, this isn't more data, right? We were not introducing more information about mappings between doctors writing notes and outcomes in the world. What we're just doing is embodying some knowledge or some assumption about the causal mechanism of the data that we got under interventions on E. We're just, instead of modeling it through regularization, through something to do with the architecture of the model, we're modeling our problem through the data, and this is what the data should reflect. And because of that, we should only see performance gains on our solution. All right, so what do we see when we actually take this to the data? This is, here you can see methods from the literature. They include like the best causal approaches like IRM or reweighting. They also include methods from the domain adaptation literature like distribution robust optimization. And if you compare it to our approach, you can see that while we're not getting anything in distribution, so we're not better at predicting within mimic or within Beth Israel Hospital clinical conditions, we're doing a much better job with a much lower variance when we get to see another hospital. And obviously, we've introduced a lot of errors. I'm sure there's a lot of mistakes in when we've generated these notes, but you should also compare it to the baselines to get a clear image. The same thing happens in other important clinical notes tasks that we saw. Yeah, you see, there's no gain in distribution. There's a lot of gain out distribution with very low variance.
So,
yeah.
So what's the, ultimately, what's the approach? What are you actually?
So what you're seeing here is a different approach. What we're doing is we're generating more training data based on this causal estimation technique. You then train the same model you wanted to train anyway with all examples that you have in the training set and all of the generated.
So this is just not just, but it's data augmentation.
This is literally data.
So what's kind of the new thing about the data augmentation?
So the new thing about data augmentation is that the way we do augmentation is based on the causal structure of the data, and the method for augmentation is based on, I showed you a different approach, but you can also think about other causal estimation techniques of how you're gonna generate this unit. So the way you do augmentation is different, and it kind of follows the causal structure of the problem. And you can also, because of that, you can also derive a lot of more principled ideas about why it works. Unlike augmentation, we can just do something and hope that it works.
And how it relates to the bound that you showed us earlier?
So it relates to the bounds in the sense that we can connect.
These are not but two bounds for two different.
These are two different methods. This is our approach, and this is kind of best performing in terms of sample complexity.
These are algorithm independent, right?
These are different algorithms.
Oh, so it's a different bound for different algorithm for different.
Yeah. This is sample complexity for our approach and sample complexity for the best performing alternative.
I see.
And what we're trying to do here is to give you a way to theoretically think about errors that you're going to make in imagining counterfactuals. So we're connecting the causal quantity. This is unobserved. We're connecting the causal quantity to what you're going to expect of your model. So this is connecting causality into that sample complexity.
Question?
Yeah.
I'm missing something. The doctor's notes are very central in your project.
Yeah.
It's all the use of language model.
Yeah.
Are they really the key factor?
Oh, yeah. So I think what's interesting with clinical notes is that so the only thing that you're obliged to do in a setting in an American hospital is to write everything within the note. So you end up with a lot of information within the note that does not lie in any other place. So for example, let's say the patient looks a bit pale when you look at it. There's no way of observing that other than writing the notes.
Okay.
And conversely, all of the information about the lab results is usually within the note. A lot of it is within the note.
But presumably the doctors, the physicians, view the notes as an unstructured way to describe what's essentially structured data, except they don't have a form to fit it in. So for example, whether I'm pale or whether my skin is soft or spongy, it's structured data. Maybe they have slightly different ways of expressing it,
Yeah.
not unstructured data.
No, so
So an alternative would be to structurize this.
an alternative would be to structurize all of this information. So any type of kind of weird type of kind of unexpected type of information could have an variable of its own and could represent it. Paleness could be a variable that's structured for sure. The situation with clinical machine learning in the US at least is that we're very forward to that solution. But yeah, you could imagine that certainly.
So I'm confused by the fact that you said that all the labs are within the notes, but at some point you said that you are already also adding the drugs and the notes.
So what they might do when they're like lazy or whatever reason, they would just paste it within the note, and this happens sometimes. There's no rule for them to do it or not to do it, so they often do it and they often don't. And also, regardless, what you don't get to see in the notes is prescriptions that they get throughout their journey, the medication that they actually take, compared to what they were prescribed with, and a lot of other things. So there's a lot of M information that's not in X, but there's certainly some M information in X, which is fine.
It could also be that they're putting in the notes the lab results that
Oh,
they
yeah.
think are more significant to the decision. So there is data
Yeah.
or information in what they copy into the notes and what they don't copy.
Yeah, the way to do the structure is that if you read it, you should be able to make a decision based on that, not on the other information. So there's definitely that thought process that goes. That's important for sure. This is why one of the reasons we want to use clinical notes when we make decisions in hospital.
I have another question. Yeah, a question about, so I'm still wondering about the actual data augmentation you're using. So maybe you can say a few words about how it resolves the issue about high blood pressure for that.
Oh, yeah. We will match patients based on this information, either because it's represented in X or because it's represented in M. But we will be able to only augment data for pairs that already have the same blood pressure. So we can think like in causal terms, we're only controlling for that variable. We will never ask the counterfactual estimation process to produce us counterfactuals for patients with different blood types. So there's no variance.
So you won't be able to generate data for.
For that, so those two patients will not get matched. We will try to match two different patients, two different children with similar blood pressures and do the notes for them. So there will be a lot of notes that we won't be able to match.
So you initially you're taking only patients that are close in some.
Yeah, there's propensity scores are there. They're similar in some instances.
And isn't that a large part of the? I'm wondering whether
Matching, yeah, no,
matching,
certainly, so matching is
like
crucial.
understanding the
Yeah.
metric.
Yeah, you think of it like in causal terms, we do matching a lot because we want to approximate the treatment that we never got to observe. So if we get patients that are very similar apart from the doctor that they got, you can think about this as they could have been randomly assigned a doctor because other than the fact that they have a different doctor, they look identical. And that's the entire process we want to do in causal. This is what we're trying to bring. So matching is definitely the key aspect.
So you have it's a very simple technique. I mean, it's not like you can imagine a more sophisticated.
Right, so you can, it depends on the causal
samples and say.
Yeah, it depends on the causal structure of the data. But in this example, it is quite straightforward. That's the benefit of that. That it outperforms a lot of strong methods with thousands of patients with a very simple. That's, I think, one of the promises of that. We can do this type of things. I want to summarize a bit what I said so far. So that literature of trying to remove shortcuts through some causal notion of the world is focused primarily on enforcing independence between this e variable, either observed or unobserved, in the world. We imagined some causal graph encoding our assumptions about the world, and we got some shortcut removal method, but it was usually very hard to optimize and needed a lot of samples to actually work in reality. As an alternative to bypass some of these challenges, we have focused in the past on calibration as an alternative that kind of circumvents our need to do independence testing, but was still very hard to do in practice. It does provably remove shortcuts, and the literature has kind of expanded on this notion since us, but we have moved on. I then showed you that you can model the causal mechanism through augmentation, and depending on the causal structure, you will design the augmentation technique that you want, but it will depend on the causal structure. This might become plausible now with very strong generative models that represent high-dimensional signals. And I've showed you that this could get you better cycle complexity, and empirically it performs much better. All right, so I have a couple of minutes, I think. I wanna wrap up with the Congress relationship. This is just a case about the freedom of causality. So let's skim through it very quickly and all right, so get out of the hospital case and imagine we are social scientists, we have a goal, we want to estimate the causal effect of political ads on voting outcomes, right? We have maybe a marginal ad by Donald Trump. We want to, but before we're deploying it in the world, before we're spending some money on it, we want to think about what will be the effect on voting outcomes. And this is a very common question in sciences. And text, you can imagine here is our treatment, right? We're producing some text and hoping that it will have some effect on our voters. Right, so if we just think about this from a machine learning perspective, especially in NLP, let's just naively embed text with a language model. I showed you before. To do it, we get some vector representation of text that it's very expressive, but it's uninterpretable, and there's no way of kind of explaining to a social scientist what are the assumptions that I've made to get you this vector representation. It also gives us a very weird problem in the world, which is what is the causal effect of this vector? What does it mean to be more of that vector in terms of effects on voting outcomes? So the way that social scientists think about machine learning to solve this problem is just learn an interpretable representation, use it as treatment. And what this led us to is that topic models, or LDA, a model from the early 2000s by my postdoc mentor, is still the main workhorse for this entire literature. It gives us, it's a probabilistic model that gives you a semantically expressive representation of text. You get distribution of the topics. It is interpretable in that sense, and you understand the assumption. Or you can show you the graphical model, the probabilistic model that gave you this model. And this is something social scientists really like, and this is why they're still using a model that's independent of what we've been doing in the last 20 years. But the challenge for these types of models is that they need to be suited to the causal problem, right? It's not like any problem could fit this simplified causal problem. And one of the project that we're working on now is exactly that. It's trying to suit the problem, the model to the causal problem. So what we get to see in the world with these ads is that they're not identically distributed across channels, right? The distribution of ads on Fox News is surely very different in terms of what they get to see compared to what CNN gets, right? And we can't imagine that training a model on these entire group of channels would get us just a single abortion problem or a single immigration problem, because the way Fox News talks about immigration and Fox News talks about abortion is very different than what CNN is. So that's a problem for machine learning and leads to a very kind of suboptimal solution. In terms of statistics, the representation error will cause estimation bias. And what we're trying to do to solve it is to introduce an environment in the same way we thought about environments before, but now in a probabilistic Bayesian model to get us kind of a separation between talking about immigration broadly and talking about immigration and Fox News. So if we put some structure on it, then imagine that there is some global distribution of topics that's diffuse, and we have a specific variation for each individual channel, which is sparse. Then we can get a model that hopefully gets us there. And for lack of time, I'm just going to show you the results. You can see that, for example, in the global topic of military, you see kind of general words about war. When Fox News talks about it, it's in the context of terrorism in Iran. And in CNN, it will be more about war that is problematic within US eyes, like Iraq, and getting the troops home. All right, so to summarize that entire issue is when we do representation for causal estimation, we need a lot of clarity about our assumptions and interpretability and the way we structure the text. LLMs are not suitable for that. They might be, and we're working on methods that might make them such, but they're not at the moment. So we need to gear the solutions that we build for the causal problems that scientists actually care about. And I just showed you one version of how to do that. All right, so my entire research is on these two connections. I've done a lot of work on robustness, which I showed you today. I also introduced the problem of explainability as a causal problem to NLP. In the converse relationship, I work a lot now on trying to improve causal estimation with text through methods from machine learning. And I think the future for it is about connecting the two and getting us an expressive and interpretable generative model that can uncover latent themes from text, generate counterfactuals, and because of that, make reliable and interpretable prediction. Thank you.